I'm currently working in a Shockwave simulation project. In that, shock will travel through the entire tube within a half a millisecond. So, to measure it and evaluate it, we need sophisticated equipment, right? So, that is expensive. I didn't went in that way. I chose to simulate it in computer. How I did it? I just designed the entire shock tube and gave computer the values of the atmosphere and values whichever it demanded. And surprisingly, computer gave the better results for what is required after the simulation. And that process is known as CFD. And I'm going to explain it how actually it is working. And not in a textbook way actually, just what's actually going on in it. So let's dive into it. CFD is nothing but computational fluid dynamics. When you talk about fluids, you might the first thing which might come into your mind might be water or coffee or juice or some other liquid. But fluid is not just limited to that. When we talk about fluid, anything, literally anything, which can take the shape of the container which is containing it can be called a fluid. Based on the density, the phases may changes, which we'll talk about later. So when we say computational fluid dynamics, we're not just talking about water moving the pipe. We are also talking about the air which is circulating inside your room, the blood which is flowing inside your veins, and the exhaust of the aircraft engine and exhaust of the rocket. Those can also be computed using CFD. So why to compute it even? You can't just go and do a manual testing of performance. When you test it to improve your design, you might get your desired result if you're lucky enough. But if your test goes on iteratively for 50 to 100 or more times, that will give you a massive bill amount, which will going to surprise you or which will going to blow your project required funds. And I don't want to do that. Most people don't want to do that. They don't want to spend more money on just improving the design, but they want to do the improvements as well. In that place, CFD. When you input your geometry and when you say the computer how it should run, it will actually give you the result which you need. And with that result, you can actually iteratively improve your design, and which will going to cost you around $0 if you know what you are doing with your laptop. Then it will be around $0. Yeah, and how it works now? How it works? To keep it simple, I split it into three phases, which is meshing, governing equations, and iteration. Meshing is nothing but your geometry which you are inputting. The geometry will be uh, split into couple of hundreds or couple of thousands or couple of millions of cells according to your needs and according to your commands, which you gave as a command for your particular solver. And that in that particular cell, all the governing equations will be calculated in each and every cell. Governing equations are nothing; those enforces the rules of physics, such as mass conservation, momentum and energy conservation, and lot of equations comes under Navier-Stokes. And those rules were the ones which shapes and replicates the exact natural conditions. Like those rules were like the rules, traffic rules, and the rules enforced by the government to us, which makes a good economy. And these things will be done iteratively till we get the accurate result. How do you know that it is accurate? How does the solver know it is an accurate result? And then by converging, solver in the beginning will be set to an initial value that will be set by a user. I mean, human, and those values usually they will be wrong. And solvers will keep on calculated, iterate every time, and until this process will goes on repeating until we reach a certain point that the previous result matches the future result, or it is coming approximately equal to the future result. In that point, everything will come to a conclusion and the solution will get converged, and that will be your required result. With that result, you can increase or improve your design or whatever the project you are doing. So, in simple words, CFD is not just magic. It's just a lot of equations, lot of physics, a lot of computation, which is visualizing what you need in an experiment. And it is not CFD is not just limited to certain cases. Depending on which physics and which work and which project, which flow which you need, it will differ, such as FSI, compressible flow, turbulence modeling, multiphase flow, conjugate heat transfer, etc. And surprisingly, when we talk about heat transfer in the laptop, there will be extra strands. The heat transfer simulations will be carried out in the computers of the particular manufacturer, and they will bring up with the particular configuration of cooler for the particular laptop, which will play a major role in the for giving a performance for our particular laptop or PC, whatever it is. So in this way, CFD is better, and CFD is useful in more and more ways, and it is actually used by a lot of manufacturers, original equipment manufacturers, and lot of MNCs, and lots of researchers who are going to make a turbine blade design or some other kind of simulation, or car manufacturers who is making cars, and F1 cars who is where the aerodynamics and the downforce were very important. They will do the simulation using CFD with the software which they have or software which they need. So that's all about CFD, and I might be wrong about certain stuff. I'm not sure. If you guys are free to comment it down. I'll do a deep R&D in that, and I'll make a sophisticated video on that particular topic in the upcoming videos. So comments are open for you guys, and in the description I gave my LinkedIn profile. You can see through it for to get connected and to get updated on my future projects. And that's all about it. See you in the next video. Bye.